And we'll PowerPoint. The book has this exact theorem. I've just copied directly from the book. So I don't know what kind of note taker you are, but like when I look at the notes that I'm going to show you today, I might want to absorb them, rather than write them. Lagrange, sorry, Taylor's theorem, or we're going to focus on something called the Lagrange error bound. You can say it all front sheet back. Lagrange. People in the back, if you haven't gone yet, you should get some food quietly. Okay. So sorry, the title's not at the top. It's not my usual. Good job of that. So let's start by doing something that you do know how to do, and one of the big focuses today is the error. Like this is like one of the big things that we need to start talking about is error. And eventually we want to like kind of readdress the question of when things converge, because we've been very excited to do all the things we've been doing recently. We're like, yes, I can take any function and get a Taylor polynomial. But we still have all these questions about how well it converges and when if it even converges at all. And these are all like really excellent questions to ask. So we're going to start like getting into that with some more talk about errors today. So let's use the fourth order Taylor series for this, which we can just write down, can't we? We should just be able to write this down. I don't need you to expand it out or anything, but at this point you should be able to just write this down. The Taylor expansion for this is for e to the negative 2x. For e to the u, it's 1 plus u squared over 2 plus u cubed over 3 factorial, etc. So what's e to the negative 2x? The Taylor expansion is 1 minus 2x. I assume this is kind of review. Over 4x squared over 2. I don't know how much I want to simplify yet here. 8x cubed over 3 factorial. All of these can be reduced, but okay. So you're just plugging in, you're just plugging in negative 2x everywhere you see a u in the top line. Okay, so that's not meant to be the interesting part here. All right, we're going to think about now plugging in 0.2 to this. And does it say? It says use the fourth order Taylor polynomial. So we'll use, we'll do what it says. And what would you like to call that? Maybe we call that T4. Yes, is the notation we've been using. So actually I need one more term here. I'll write it here. It's 16x to the 4th over 4 factorial. So we'll use just those first 4 terms there. We'll use just those first 5 terms, the fourth order though. So I don't need to fill that in necessarily, but someone can tell us, and maybe some other person can do it too, and we can make sure that everyone gets the same answer here. Have a calculator. Feel free, by the way, if you need to refill your plate, just get up at any time. Quietly. Thank you, everyone. Yeah, thank you guys for this. Especially really good. There it goes. I got you.
So what drink are we allowed to run? There's only one. Oh, it's only this one? Yeah. There's not allowed.
1 minus 2 x.
I got 6,794. For the Taylor, for the fourth order. Mr. Chase, can I go throw this on the water now?
Oh, wait. I'm not sure both want. It's a wild segment, man.
Yeah. Did you 0.6704?
I'm feel with the new hardware. Make sure. Wait, that's not what I got. 1 minus 2x plus 4. Oops. That's right. 2x to the second. Did you get 0.6704?
Yeah.
Okay. 0.67 0.704. By the way, I just typed this into y1 and then evaluated it. Okay. So good. And then the question is, what is actually e to the negative 2 times 0.2? Someone do that too and tell us how far off we are. We're not very far off, hopefully. Now, this is a function of the fact that when will we get a number that's really far off? So the actual value I'm getting is 0.6703 approximately. So yeah, we're on the order of 10 to the negative 4 off, right? Like we're not very far off is the point. So this should like already lead us to think like, okay, so how good do these get? Like I'd like to be able to like in life use at all times maybe the fourth order Taylor polynomial and forget the function. How badly will I be doing if I just make a practice of doing that? Is the question today. Yeah, dude. Yeah, there are two things that kind of control how good of an estimate it will be. One is how close you are to the center of the expansion, and the other is how many terms you use, right? So those are definitely important. So here it is with all its glory. Like I said, this is in your book, and it's a little scary to look at, but I want to make sure you like absorb it. So, all right. So the first part should not be a surprise at all. Read the first line with me here. This is just like what we've been doing. But notice that there's not like a dot, dot, dot at the end. This is a finite polynomial that you're looking at right now that terminates here with one last term. And we call this the error term. Okay? The error of order n for the nth degree Taylor expansion. And it has the following form, which actually kind of looks familiar too. So you understand, I want to make sure you understand. We've like truncated the series, and we've added this like error term to the end. So this is the thing I want to draw your attention to the most. Everything else should look familiar. We've got the Taylor polynomial of order n, and then what we're claiming is that this is equality. This is important, right? That this is not just like an approximation. On the previous slide, I was using like a squiggly equals, right? The approximation to say, you know, certainly if I cover this box down here, then it is an approximation. But what I'm saying is that maybe there's some error term that we can add that makes this perfection, that like corrects this and makes it perfectly equal. That equal sign is not a mistake. And the form of the remainder looks like this here. This is called the Lagrange form of the remainder. And notice that it looks very familiar, doesn't it? It looks like just the next term. This is the nth order Taylor polynomial. And we're saying that there is a term that has the same form as the n plus first term. Yeah, that is in fact what we're saying, with one small exception. Do you see it in there? The c. All right, this should feel a little bit familiar. Even the use of the c should sound a little familiar. This is an existence theorem. What we're saying is that there is a c in the interval containing a. This is the part that now returns all this language at the top. There is some value in between a and x such that if we evaluate it there instead, we get perfection. We actually that corrects any mistake that might be. We don't have to go out to infinity. It's exactly it. Yeah. And this should remind you, that kind of existence statement should remind you of there exists a c. Should remind you of the mean value theorem, right? And in fact, for the constant approximation, this is the mean value theorem. Let that like sink in a little bit. That is, if I just have all this removed, if I just say, oh yeah, really? Is it true that f of x is equal to, let me write it for the first case, f of a plus some error term of the form f prime of c over 1 factorial times x minus a to the first. Is that right? This is the super trivial case. This is when we only have the first term. I'm saying this is the error term, right? I'm saying there exists some c that perfectly corrects and makes that equation not just approximately but perfectly true. And do you see that that's actually the mean value theorem in disguise? Solve it for f prime of c, and you'll see it. Solve that equation for f prime of c. What does it say?
Oh, that is.
Solve it for f prime of c in your head quickly. What do you get? You get f of x minus f of a all over x minus a, which is the average rate of change. I'm just saying, so this is like a generalized form for any order. This is like a pretty powerful idea that we can like generalize. It also maybe sketches, maybe that suggests a way in your mind that can prove that too. Okay. So that's the kind of thing, if you remember it like this, it wasn't like we're not kind of sure, we're not kind of sure, we're definitely sure that a C will exist that will exhibit this property, will correct perfectly the series. Okay? And yes, it should remind you of the mean value theorem, because in some way it is the mean value theorem. So, again, this is a pretty powerful idea that such a term could exist, and all we have to do is select the right C value. In practice, just like we do with the mean value theorem, for any given problem we might look at, you can actually solve for that C value. I don't think there's ever really a time in our lives where that's going to come up in any problem that you'll see where they ask you to find the C value that makes that true. But it's a comfort to know that it exists. Okay. All right, this suggests, though, something interesting. On the interval of interest, where we might be living, in particular, you might have the center A, and we might be interested in estimating values of our function as far away as some x value x. Well then, I'd like to at least know maybe I don't care about getting it perfect. I know that maybe there is such a value of C that would make this perfect. But at the very least, I'd like to know how bad I could be. Okay? And the answer is, I don't know what C is, but if I just let C be any value on the interval of interest, how bad could it be is my question. On the interval, how big, the question is going to be that's going to come up on the next slide here, is how big can this thing be? Everything else is completely determined, isn't it? The only unknown here is this. And so my question that's going to lead to the next result is, how bad could that thing be circled there? And the answer is, on the interval, we can just figure it out. We can figure out how big does this n plus first derivative get on the interval of interest. And whatever the answer to that is, we'll plug it in and we'll have an error bound that's sure. So that's really the way we're going to go with this, even though it would be fun to find the C value for any given value. We're gonna mainly be thinking about error here. Okay, so notice this is the same thing we just talked about on the last slide, except I've replaced the thing I circled by capital M. Okay, where capital M is has this property. That is, it's the maximum value in absolute value that the n plus first derivative could even be on the interval of interest. And so what we're saying is that if you're using the fourth order Taylor polynomial to make estimates of your function on the interval, I don't know, how about the interval 0 to 0.2, right? That's the one we were just doing. Then the worst it could possibly be, that we could ever be, no matter where we are in that interval, is this. And by this I mean the max, where this thing here, where this is 5 factorial, and this here is x minus a to the 5th. And the m is the maximum value of the absolute value, the maximum of the absolute value of the n plus first derivative, the 5th derivative in this case. So I'm going to actually return to that example where we are going to e to the negative 2x. And we're actually going to show you this and see if our error that we got was inside the bounds that this claims it will be. Okay, that's what we'll do in a second. And by the way, just as a footnote, this is a little different than the formula that appears in your book. So it's a little easier than the one that appears in your book. But I would challenge you to look at the one in your book and think about what they're doing maybe. But I think this will serve you well. It'll be the best thing you'll ever, it'll be good enough for what we're needing. Well, I think this is like the critical piece here today. Even like I said, we're going to be mainly concerned about error. And that's called the Lagrange error bound, right? The last thing, Rn, we called the Lagrange error, that form of the remainder. So this is called the Lagrange error bound. A lot to take in so far. I mean, I promise, we are going to return to some real numbers in a second. So, but even then, can I clear up the notation for you, or the concepts, or as we
So when you're calculating RSA, you're just calculating the error that you then add on to the regular.
Yeah, it's going to be the amount plus or minus, right, that it could possibly be off by. Like maybe this will come out to be like 0.0001 or something, and we'll be like, oh, if we're using the fourth order Taylor polynomial on this interval and making a whole bunch of different estimates for f of x values, we know with confidence moving forward that like there will never be a time when our estimate will be more than whatever this tells us, 0.001 off or something, you know, just comforting.
When you write your final answer, you would write what the approximation is plus or minus r sub n.
Yeah, I mean, depends on what the question asks. Sometimes it will ask you for this number, in which case you just give this number. You know, you say, we're within this amount. So here's an example we just did. Notice here I just copied the thing we did before. We calculated the fourth order Taylor polynomial, and we plugged in 0.2, and this is what we got. I have it in lots of it, so lots of its glory there. And our previous theorem, what our previous theorem says is it guarantees that for any x value in the interval 0 to 0.2, that the error will be no greater than this. Okay, so this is let's make sure we understand where each number came from. Where does the 5 come from? Why 5 factorial? We're using the fourth order Taylor polynomial, and we said it's n plus 1 everywhere. So this is 5 factorial. This is also an n plus 1, so that's a 5. Where's the 0.2 come from? Remind me, that's the x value we care about, like x minus a here. And 0 happens to be the center, but if it's something else, then that would be there, okay? And then the only big question I still have is, like, where did I get that 32 from? So we'll address that in a second. Michael first.
Could you not just plug 22 into f of x and then subtract that?
Yeah, if we care about exactly at 0.2, we can actually, like, find the exact error at 0.2. Yeah, but this is a more powerful theorem. This is saying that anywhere on the interval 0 to 0.2, we're going to be guaranteed that our error will be no worse than this, no matter where we are on the interval. So if you happen to be at the end, then that will be true too. And we actually computed it. For any given value, you could actually compute the error if you have the original function.
Yeah.
But here's the thing, especially as we think about like functions we don't have access to. And here's another thing. Sometimes we don't even have a function. If you can believe it, there'll be some times when all we have is the Taylor series in our hands. Someone might just give us the infinite series. So if you don't have the original function, then what can we say about the error? We don't even know what the original function was. So there are lots of cases where this is going to be all we can get. And we can still, even though we don't have the original function, we can make claims about the convergence of the series. Like pretty nice ones. So is this within that range? Well, sorry, we didn't go, let me go back and get that value. Where was it? How far off were we? It was 0.0001, I think, like that. 0.00. It should be bigger than that. I'm gonna make sure I'm not lying to you. I have to go back and check, but this should be inside that. Where 32 is the maximum of f, the fifth derivative of f on this interval. And even without calculating, we justify what that value is going to be. Let's see if we can think about this together. This function, the fifth derivative is this. Do you agree? Notice we need to like bring the fifth derivative into this discussion, even though we didn't up here, right? So I just wrote down the fifth derivative. I'm asking what is, in absolute value, what is the largest that will ever be? Well, what does this look like? I'm actually going to think about the picture on a lot of these. That is, without the absolute values, well, actually with the absolute values, what does this function look like? Yeah, it's actually just an exponential decay function. So on the interval 0 to 0.2, where will the maximum value be, just like from what you know? It'll be at 0, which is convenient, because even without a calculator, I know what the value is here. If you plug in 0 for this, you get 32, or an absolute value 32. So I know, in fact, this value right here is 32. On the interval, again, on this little interval, 0 to 0.2, right? We're looking for the maximum of the absolute value of the n plus first derivative. Okay. And then once we get that, we call it capital M, and then we say this finally. And again, that goes back to the fact that we have there is some C value that makes it perfect. But let's not bother finding what it is, as we don't know maybe. Well, what could C even be? What kinds of values could C even be? The existence theorem guaranteed that a value C is some value in between 0 and 0.2. So let's just, we don't know what C is, but let's just consider all values. What could it even be? And the answer is it could be no bigger. It could be no bigger than 32, the fifth derivative. So I don't know what C is, but that thing up there couldn't ever be worse than 32. So that's the way this goes. This piece of the puzzle, by the way, was actually fairly simple here, even though you might have had a little headache thinking about how we got 32 in this particular case. It's actually, this is not bad. Sometimes it's a real headache. Sometimes we really need to look at it with our calculator. Sometimes, yeah. It might be an optimization problem, really, right?
Oh.
I mean, find the maximum of something on an interval. It might check endpoints. I mean, I don't know how terrible we're going to make those. A lot of times you'll have access to a calculator, so maybe you just graph the absolute value of the n plus first derivative and just look, right? Is usually what we'll probably end up doing, or maybe we can reason to it like we just did now. But it could be that particular problem could be pretty bad, just that one question.
Did we get 32 by taking the first derivative on that?
Yeah.
So why would I do
Yeah, I'm just saying, how would you find the maximum value of the fifth derivative on the interval 0.2? Right now, this could be enough because we knew what the picture of that function looks like, and we're just, oh, it's going to be the left endpoint because it decreased. We have to know it. But like really, you might have to like think hard about the.
Wait, can you just look at the signs of F prime and F double prime? Find out if the graph on
You have to look at the signs of the sixth derivative and seventh derivative. Yeah. Like if you're working on trying to find the max of the derivatives, yeah. But like I said, I don't think that discussion will come up too much. We will often like hand you a calculator as you're working on that, and so. All right, find the maximum error when this is used to approximate that. Apparently, this is the Taylor expansion, the of order 2 for this. I don't know if we derived that one in class. I think it did come up actually, maybe. Maybe back when we were doing geometric, this is a good one to take the derivative of. Remember all that? Okay, so that's how you might have derived this, but that's not part of the discussion right this second. You can go back and think about why this Taylor expansion is this here, okay? The conversation right now is let's find the maximum error when this quadratic is used to approximate this in the interval negative to positive 0.1. And we can actually go to negative 0.1. This is defined for all those values, so I think we're okay. Yeah. 0.9, it will be the argument of the log. So, all right. So let's see if we can say something at least here. The first thing we need is the first 3 derivatives, right? We need the third derivative in our hands, don't we? Because we're going to calculate the error bound. Well, we're using, it said find the maximum error when the order 2 polynomial is used. So what we need is, you forget, let me not tell you that you need it. And then you'll see as we do the error bound, how do we do it? We did capital M, whatever that is, we'll have to figure it out, divided by n plus 1 factorial. So we're talking, that'll be 3 here, everything, and M will be the maximum of the third derivative on the interval. So, yeah, Michael.
How do you know that x minus x minus 2?
Say that one more time.
The x squared minus, no, that x.
Oh, how would we know that besides me telling you? I mean, one way to know it is because I told you could trust me. But if you wanted to get it yourself, there are 2 ways you could come up with this Taylor polynomial here.
That's the, what is that?
Huh?
Is my question.
I'm just saying the first 2 terms, if I asked you, find the Taylor expansion, please, Michael, for this, ln of 1 plus x, go. And you should be able to do that. There are 2 ways you could maybe do that yourself. One of them would be to take derivatives, right? And it would be the nth derivative over n factorial times x to the n, all that. Yeah? Is that good? Or you could recognize that this has as a derivative a geometric thing, and kind of maybe hack it a little bit and take an integral, all that. method, one of those ways. Somehow you would come up with a series though. I know, I trust you. And the thing you would get is this. For the first two terms. If you want more, you can get it because you're good at that.
So how do we?
I'm just telling you just quick at the time that that's what you'll get. Alright. So now we'd like to really consider the maximum of the third derivative, this thing right here, on the interval negative to positive 0.1. So, that's a rational function. I mean, we really have to kind of think hard about this, actually, right? Even this statement is not obvious unless we have to think about the graph maybe for a second. This has a vertical asymptote. This is 2 over x plus 1 cubed. It has an asymptote at negative x equals negative 1. And it decreases after that. You could like think about it.
Please pardon the interruption for a brief announcement. Seniors, this is a reminder. If you are interested in speaking at graduation, you should plan on attending the interest meeting being held tomorrow, Tuesday, March 15th at lunch in the main office conference room. 2 seniors will be selected to represent the class of 2016. If you have any questions, see Ms. Weaver or Ms. Hyler. Thanks so much.
Alright, so I-plane this decreases. I think you can get this with pre-calculus knowledge by coming up with a little picture of this. Or on your calculator by graphing a picture. Or if you really wanted, you could use like the first derivative test and take the fourth derivative and check and all that, right? One way or another, convince yourself that this has an asymptote decreases here. Therefore, actually like the last one, the maximum value m, capital M, for this will be whatever the value of this function is at negative 0.1, I say. Plug that in to get your error.
Mr. Chase, do you know what the homework will be?
I can go back to that slide, yeah. Alright, so I apologize for the quickness of this, but I think you're in a good place to be able
Will
to
the following
compute
students please come to the
the
main
error
office?
on a given
Arnold
interval
Babcock,
using the Lagrange error
Jacob Van
bound.
Longhausen,